Welcome to our video about line integrals. Basically, line integrals can be used for finding total mass of a wire whether the density along its length is constant, or to find work done by variable force along a curve, which is very notable, for so far most of us have only encountered work done by constant force, the simplest case only. First, for these reasons, line integrals are more general than the integrals within some defined intervals we learned in Calculus 1. Suppose that we wish to integrate over the curve C which lies within the domain of some function, say f(x,y,z), which is parameterized by rt equal to gti plus htj plus kdk, where t values range from a to b. We're going to integrate this composite function f(gt, ht, kt) with respect to arc length from t equal to a to t equal to b. So, we first partition the curve C into n number of subarcs, just like one shown here, with the typical subarc having the length of delta sk. In each subarc, we choose a point xk, yk, zk and form the sum over here. As n approaches infinity and delta sk 0, then we will have our definition. Note, however, function f has to be continuous. The first derivatives of functions gt, ht, and kt must be continuous as well. Here we have the line integral of f over curve C. Notice that this integral is with respect to ds. Previously, we learned that ds over dt is equal to the magnitude of v. With some modifications, we get ds equal to magnitude of v dt, just like the one over here. By substituting ds equal to v dt, and suppose that t values range from a to b, then we have an integral with respect to dt with the upper limit as a and the lower limit as b. Now, let's turn our attention to an example here. In this example, we are asked to evaluate the line integral of 2xy plus 3z over the curve C from point 0, 0, 0 to point 254. First, we find the vector rt between these 2 points. So just deduct 2 by 0, then we will have 2i. We then deduct 5 by 0 to get 5j, and finally 4 by 0 to obtain 4k. From rt, we can generate the parametric equations x equal to 2t, y equal to 5t, and z equal to 4t, and t values range from 0 to 1. Next, when we look at the formula at hand, we have to find the function f(gt, ht, kt). This can be easily done by substituting x equal to 2t, y equal to 5t, and z equal to 4t into the function given by the questions, which is f equal to 2xy plus z. By doing so, we will get 20t squared plus 12t. After that, we need to find the magnitude of v, which is equal to the square root of the sum of the square root of first derivative x, the square root of first derivative y, and the square root of first derivative z. From the parametric equations we have in the previous slide, we get the derivatives of x, y, and z equal to 2, 5, and 4 respectively. By substituting these values into the formula, we get the magnitude of z equal to square root 45. Now that we have all the components needed to use the formula, so by substituting everything into the formula, we will get the integration of 20t squared plus 12t times square root 45 with respect to dt. Since square root 45 is a constant, we can place it outside the integral. After doing the integration and substituting the limits, we will get 38 square root 5. One useful property of line integral is that the integration of a function over a curve C can be the sum of the integrals over the smaller curves that make up the curve C. Therefore, we have a formula here. Let's do an example to get an insight of it. Figure below shows a path from origin to point 111. The path is the union line segments C1 and C2. We need to integrate fxyz equal to x minus 3y squared plus z over the union of these line segments. We first have to find the vector rt and define the interval for t and find out the magnitude of v for both line segments. These are the data we obtained. Notice that the rt for C1 is ti plus pj. Z is equal to 0, and both x, y varies in this case. While the RT for C2 is I plus J plus TK, because in this case our xy coordinate is 1, 1, and only Z varies. The intervals for T in both line segments are the same, which is from 0 to 1. The magnitude of V for C1 and C2 are square root 2 and 1 respectively. By using the formula and substituting the data in the previous slide, we have the sum of the integration of ftt0 times square root 2 with respect to dt with upper limit 1 and lower limit 0, and the integration of f11t times 1 with respect to dt with upper limit 1 and lower limit 0. ftt0 will be equal to t minus 3t squared, and f11t will be equal to 2 plus t. Now our integral contains all the necessary components. By performing integration, we will at length come to this answer, negative square root 2 minus 3 over 2.
In our next video, we will be talking about more of the intuition behind the technique of line integral. So, see you there.